My name is Xian Chen. I'm from Peking University. The title of my talk is Distortion of Gravitational Wave Signals by Astrophysical Environments. Let me start by showing you our concept or our understanding of compact objects before LIGO-Virgo detection of gravitational waves. Here, the purple dots are black holes and the yellow ones are neutron stars. At that time, we know almost no black holes more massive than 20 solar masses, stellar origin black holes. And between the black holes and the neutron stars, there's also a mass gap residing between about 3 solar masses to 5 solar masses. LIGO and Virgo completely changed our view of compact objects. Now, the blue dots are binary black hole mergers detected by LIGO and Virgo. You see that even before the merger, many black holes are already more massive than 20 solar masses. These black holes have never been seen before in X-ray binaries or other binaries detected by electromagnetic waves. Also, between the lower mass gap, there are also interesting objects detected by gravitational waves. Many people are trying to explain this, and they study the formation channels for binary black holes and try to understand how massive black holes can form and then incorporate it into binaries. But when my collaborators and I looked at the results, we were asking ourselves a completely different question, which led us down to a completely different path. The question we were asking ourselves were, how are masses measured in the first place? In the end, what we detect is a signal like this. This is a wave signal, and it has a magnitude and frequency. The frequency also increases with time, so it's a chirping signal. At best, what we can get from a signal is 3 observables: amplitude, frequency, and a frequency dot. If we wish to infer the real physical parameters like the masses of the black holes and their semi-major axes, we have to rely on model. This is one model, which is using the inspiring part of the signal. If we do a clever combination of the frequency and the frequency dot, we can eliminate the dependence on semi-major axis and get a mass scale, which is called the chirp mass. And we have another observable left, which is the amplitude. We can further use the amplitude to infer the distance, because further away is the source, the smaller the amplitude is. So this is how we can infer the mass and the distance of a gravitational wave signal, or more exactly, a chirping signal. But the universe is more sophisticated than that. There is redshift everywhere. For example, the expansion of the universe induces a cosmological redshift. What redshift does is stretching the signal. So in the end, what you observe is not directly the intrinsic frequency, but the redshifted frequency. The frequency dot is redshifted even more, because of the time dilation effect. In the end, if you wish to use the observed quantities to derive a mass scale, the mass scale is bigger than the intrinsic mass by a redshift factor. This is called the mass and the redshift degeneracy. Without knowing the redshift, without an independent way of measuring the redshift, there's no way you can tell the real mass. And the mass that you can infer from the signal is always bigger than the intrinsic mass. Since I am an astronomer, I know at least 3 redshifts. Because cosmological redshift, there's also Doppler redshift if the source is moving very fast, and also gravitational redshift if the source is residing in a very deep potential. So why haven't LIGO and Virgo considered the later 2 possibilities when interpreting the massive objects? This is a question my collaborators, Li Shu and Cao Zhoujian, were asking ourselves at the beginning of this project. There is a reason. As I have mentioned before, people think that binary black holes form in galactic disks, bulges, or in star clusters. In these environments, the velocities is small, much smaller than the speed of light. So people think the Doppler shift can be neglected. On the other hand, the potential is not very deep, so people also ignore the gravitational redshift. But this view of binary black hole formation is incomplete. In the recent years, many works showed that close to the centers of galaxies, especially when there's a supermassive black hole, the merger rate of binary black holes can be enhanced by a large margin. The reasons are manifold. For example, close to supermassive black holes, the escape velocity is large. So there's a natural larger density of binary black holes in there. And the possibility of forming binaries is also enhanced. If there's gas, as you will have close to active galactic nuclei, then gas will exert a hydrodynamic drag and lead to a faster merger of compact objects like binary neutron stars and binary black holes. And because of all these reasons, we think it is possible that some binary black holes are merging very, very close to supermassive black holes. If this happens, then you will naturally have a Doppler redshift because the source now are orbiting supermassive black holes with a large velocity, and also an additional gravitational redshift because now the potential is very deep. So the measured chirp mass will be bigger than the intrinsic chirp mass by an even larger factor. How large these factors are depend on how close the sources are. So I asked the student, Zhou Zhiqing, to simulate this effect. Here we put binary black holes on all kinds of orbits close to a supermassive black hole, and we view the gravitational waves from different angles. The colors here show the redshift velocity. We can see that some sources are redshifted and some are blue shifted. And what's interesting is that the maximum redshift velocity is a third of the speed of light, meaning that the redshift due to Doppler and gravitational redshift can be very large. Of course, the real limits are imposed by the stable orbits. If our binary, such as this red dot here, is on a circular orbit, then the closest orbit is determined by the innermost stable circular orbit. When the central supermassive black hole is not spinning, this orbit is at 3 spatial radius, and the velocity is very large, 0.4 speed of light. Then the total redshift we can get is at a maximum 1.9. On the other hand, if the binary is coming in on a hyperbolic or parabolic orbit, then the innermost orbit is imposed by the innermost bound orbit. The closest approach is 2 spatial radius. The velocity is even higher, 0.7 speed of light, and the total redshift due to Doppler and the gravitational redshift can be 3.4. Interestingly, these factors, 1.9 and 3.4, is a factor between the black holes observed by gravitational waves and the black holes detected in the past using electromagnetic observations. Not only do we overestimate the masses, but we also will overestimate the distances because you think it's a source very large at a large distance, but actually it's a small source at a very small distance, close to a supermassive black hole. Can these binaries form in the end close to supermassive black holes at that small distances? So we reviewed a lot of literature and found several models actually predicted such kind of things. For example, in Asian disks, people know for a long time that it will capture a lot of single stellar black holes in it, and this is a place where naturally binary black holes can also form. There are recent works suggesting that the merger rate can be as high as 10,000 per cubic parsec per year. There are a lot of trapping radius in these disks where binary black holes or single black hole naturally concentrate. One of the innermost trapping radius is almost around the innermost circular orbit, 3 spatial radius. Here's a model produced in the 1990s showing that wherever you put your single stellar black hole, it will migrate towards a stable orbit, very, very close to 3 spatial radius. This is because close to a supermassive black hole, especially when the accretion rate is high, the gas is super-Keplerian. So they are pushing the stellar black holes forward because the stellar black holes are moving on Keplerian orbits. On the other hand, gravitational waves is taking away angular momentum and energy. So the loss of angular momentum due to gravitational wave is compensated by the gain of angular momentum by accretion onto these stellar black holes. And this leads to a stable orbit close to the ISCO. So we use their model and plug in the parameters for binary black holes in AGN disk, and we found that the trapping radius for binary black holes is very close, about 15 threshold radius, depending on the parameters of the supermassive black hole and accretion rate, etc. There's another model. For a long time, people know that binary black holes forming far away from the supermassive black hole can be scattered through the supermassive black hole and tidally disrupted. In the end, there will be one stellar black hole left behind, circling around the supermassive black hole. And this is a way of forming the so-called extreme mass ratio in spiral, which is an important source for the LISA mission and also the Chinese Taiji and the Tianqin mission. However, if the binary black hole is scattered not too close to the supermassive black hole, then the tidal force is not large enough to completely separate the binary. It will actually convert a little bit of the orbital energy into the inner energy of the binary, and the orbit actually can be lowered, leading to a capture of the binary. And this scenario is called tidal capture. This has been noticed by Hills in the 1990s and also Edison et al. In 2015, that such capture can lead to a lot of binaries around the supermassive black holes. We used the formula and found that after the capture, the pericenter distance, the closest approach, is 20 gravitational radius or 10 threshold radius, depending on the parameters of the surrounding star cluster and also the black hole masses. Then the next question is, after capture, do these binaries merge that close to supermassive black holes? And the answer is yes. We did a lot of scattering experiments shown in here. We see that the semi-major axis glitches whenever the binary approaches the pericenter. And on the lower panel, showing you the eccentricity, and down here the eccentricity is large, and at up here the eccentricity is actually 0 because it's plotting 1 minus e. We also see that whenever the binary approaches the pericenter, the eccentricity becomes so large that the binary will merge on a short time scale. And we estimated that this channel contributes probably 0.03 per cubic gigaparsec per year event rate. This plot summarizes the channels for the formation of binary black holes and the merger very, very close to supermassive black holes. The solid lines are the AGN disk model, and the dashed lines are the tidal capture model. What's important here is that we see a class of models which predict mergers very close to the supermassive black hole, smaller than 10 threshold radius. What's interesting is that a lot of these mergers actually reside in the LISA band, so that their orbit, the binary black hole's orbit around the supermassive black hole, can also be detected by low-frequency gravitational waves, like LISA. Because these binaries are circling around the supermassive black hole, and this is like a binary extreme mass ratio in spiral, so we call these sources BEMRIs. In the future, LISA will also detect a lot of binary black holes, like 1 to 10 years before their final merger. Then, if LISA detected massive black holes, can we say for sure that massive black holes exist? The answer is again no, because there are other effects which can affect the evolution of the binary black holes in the LISA band. For example, gas, by imposing a hydrodynamic drag, is accelerating the merger, so it will boost your F dot and leading to overestimation of your mass. Here is an example. We put two 10 solar mass black hole binary in the gas environment. Without gas, the binary will merge on a timescale of 10,000 years. With gas, the binary black holes merge on 1,000 years, and the best match template try to match the signal, tell us that from the observed signal, the chirp mass seems to be 37 solar masses, much larger than the chirp mass we put in, which is 8.7. So these results tell us that environment is a very important factor. If we don't consider them in the future data analysis, we will overestimate mass and then maybe even misinterpret the astrophysics behind the binary black holes. Thank you.